Sorry guys, my phone rang and I kept teaching because my phone was on silent, so I didn't know it was ringing and it stopped. It stopped the video. Okay, so I've gone back to where I think we kind of were. So looking at the reactions where the mass changes, where we talk about the fact that mass is conserved in an isolated system, but if we allow any gases that are produced to escape in a fume hood, hopefully, because that's safer, then we will notice an overall change in mass. So for example, if we put our reaction vessel, whatever it is, a beaker, flask, a vial, whatever it is, on a scale, okay, and we put our reactants in the beaker, we allow our reactions to take place within an open system so that our gas C can escape, can be released into the environment, and we then measure as the mass changes. Then we can use that information to calculate the rate of reaction. Okay, so for this, we would say rate of reaction is equal to the change in mass of the reactants over change in time. Okay, yeah. Okay, so then what I was doing after that, so this is now the end of your written notes basically, but after this I do want to show you a little bit more about the graphs. Okay, so the graphs that we looked at the beginning of the lesson were for if you just ran one experiment. Okay, now I want to show you what happens if we run the same reaction, but we do it twice, two different experiments. Okay, so let's say we have, let's do the same one, A, which is a liquid, plus B, which is a solid, going to C, which is a gas. Okay, and let's say we have two experiments. Experiment 1, what should we do? Experiment 1, let's use a 2-gram chunk of B. Okay, and then for experiment 2, we're going to use 2 grams of powdered B. Okay, so immediately you should be looking at this and saying, we know exactly what's going to happen. In reaction 1, we're going to have a slower rate of reaction because in reaction 2, we've increased the surface area of our reactant. This is what you did yesterday, looking at the factors that affect rate of reaction. So we've increased the surface area of our reactants, which means we should see an increased rate of reaction. Now, obviously, I don't really have anything to do an experiment for you to show it to you, but I will show you what the results should look like. So we're going to do both of the types of graphs. Okay, so let's split our page like so. Okay, so in this top row, we're going to look at a graph showing the decrease. We're just going to do one of the reactants. Let's do a graph showing the decrease in B as the reaction progresses. Okay, so we're going to do a graph where we show the change of mass of B. Okay, so we're doing basically the change of the mass of the reactants. Okay. Let's actually do that. Let's do the change of mass of the reactants because technically we wouldn't be able to know what of the mass is A and what of the mass is B, right? If we did that scenario where we measured it in a container, we put it all in a reaction vessel and let our C be released. Okay, so we're doing the change of mass of the reactants. And let's say these are in a perfect ratio so that they both run out at the same time. Okay, so what we would see for reaction 1, I need to somehow try and color code. I don't have enough colors. I've got markers coming at some stage. Okay, so reaction 1, we know what we're going to see, right? It's going to be steep at the beginning and then it's going to flatten out until it is parallel with the x-axis and hits the x-axis. Okay, so it's going to be on the x-axis because we've run out. So we're out of B and A, we're out of reactants, and the reaction has come to completion, which is why we now have a 0 gradient. Okay, so we know what's going on with that graph. Now this, okay, so this is reaction 1. Now with reaction 2, what's going to happen? We've still got the same amount of A and B, right? We haven't changed anything else. When you do a reaction, when you do an experiment to compare things, you only change one thing, everything else must be controlled. So the mass of A and B at the beginning has to be a controlled variable. So the mass at the very beginning is going to stay the same. We're going to start with the same mass of A and B. We've increased the rate of reaction. We know that. We know that using powdered B will result in an increased rate of reaction. And on these graphs, rate of reaction is represented by the gradient, right? Which means that for experiment 2, I should see a steeper gradient. Okay? Now it also means, let's think this through, if my reaction is taking place faster, that means it will be over sooner, right? My reaction will finish quicker. So if it's finished quicker, it means A and B will run out sooner. Remember, your x-axis is time. So if A and B run out sooner, here they ran out after, let's say that's 10 seconds. In the second experiment, they're going to run out less than 10 seconds. They're going to run out sooner. So it starts at the same place, it's steeper, and it crosses the x-axis sooner. We run out of reactants sooner. Okay, so this is what our graph will look like. So for reaction 2, the increased rate of reaction, how that's going to affect the graph, is in 3 ways. Number 1, we start at the same place. Okay, the mass of A and B is still the same at the beginning. Okay. The second thing is that our graph must be steeper because we know that the gradient is basically our rate of reaction. The gradient is our rate of reaction. Okay, and then the third thing about experiment 2's graph, the bottom graph, the blue one, is that it's going to hit the x-axis sooner. Okay, by sooner, I mean basically closer to the origin, further to the left. The reason for that is because we run out of reactants sooner. Okay, so if you are ever asked, and you will be asked, to do something like this, where you graph your results, and now there's a second experiment with an increased rate of reaction, what will that look like? If you're graphing the change of mass or the change in anything, a change of amount of your reactants, a decreasing graph like this, then that means 3 things. Your increased rate of reaction will start at the same place, okay? It'll be steeper, and you'll cross the x-axis sooner because we'll run out of reactants sooner. Okay, we're going to do again, at the bottom, we're going to look at what if we were graphing the amount of C. Okay, so let's say we were graphing the amount of C produced. So let's say we were doing that thing where you collect the gas in the syringe. Okay, so we know that the amount of C at the beginning is 0, right? And when we start the reaction, we've got no product. And as the reaction progresses, we're going to start with a very high rate of reaction, and it's going to slow down until it sort of levels out. Okay, so you flattens out. Okay, we know what's going on here. I'll just quickly go through you again. So we start with 0 product. We start with a high rate of reaction because the concentration of the reactants is high at the beginning, but as the reaction proceeds, the concentration of the reactants decreases, which lowers the rate of reaction. Okay, so that until we get to a point where it flattens out and our reaction is actually stopped. Okay, so this is for reaction 1, experiment 1. Now, experiment 2, we're going to do the same experiments, but now we're using powdered B, which means we're going to have an increased rate of reaction. So let's see what happens here. Okay, if I have an increased rate of reaction, I still start with 0 product. I'm still going to start here. Okay. It's going to be a steeper line, so same as with this one, it's going to be steeper because the gradient indicates the rate of reaction. So it's going to start here and it's going to be steeper, but it's going to end at the same place because the amount of C produced, it doesn't matter how quickly the reaction takes place, the amount of C that is produced is going to be the same. Okay, if I have, don't know how I can explain this. I need inspiration. I don't know. If I've got a Lego kit to build something out of Star Wars, the Death Star. Okay, let's say I buy a Lego kit to build the Death Star, and I'm building my Death Star, and someone like John is building his Death Star. Sorry, John, I just assume you're going to be much better at building Lego Death Stars than me. Okay, we're going to be building at a different rate, right? Different rates of reaction, but the final product should be the same if we're following the instructions. So regardless of how quickly it's happening, you're going to end at the same place. You're just going to get there at different times. Okay, so with this scenario, the amount of product at the end is going to be the same. We have to still end at the same place. Okay. We're just going to start steeper, and we'll get flat sooner, so we might get flat like there-ish. So we go steeper, oh, my word, terrible. Okay, so we start at the same place, we start steeper, and then we flatten out a little bit sooner, but we, I'm trying my best here. Okay, we flatten out a little bit sooner, but we still end at the same place. Okay, does that sort of look about right? But too square here, it should be rounder. Okay, something like that. Okay, so reaction 1 starts and ends at the same place as reaction 2. That's reaction 2, but reaction 2 is just steeper there at the beginning. Okay, so for reaction 2, for this scenario, it starts at the same place as reaction 1's line. Okay, so same as there. It's steeper as well, because the gradient is an indication of the rate of reaction. And it ends at the same place. Okay, so the difference between these graphs, I'm hoping you can see that. The difference is if you are graphing the reactants, it does not end at the same place. Okay, this will hit the x-axis long before that one hits the x-axis. But if you are graphing the reactants, they must end at the same place because you will finish with the same amount of product. Okay, yeah, that's basically it. So I'm going to stop this. Sorry, you guys have 2 videos to watch. I hope that you made it all the way to the end. Please do let me know if you get stuck. I know analyzing graphs is tricky. I know that. It's not the funnest thing to do, but the more practice you have with it, the more it starts making sense. Okay, oh, whoopsie, I forgot, sorry, x-axis here is change in time as well in seconds. Okay.